Good morning. I promise there is to be no laughter here. So today we'll be discussing, as Tom mentioned, I'm a little deflated because I was hoping for at least 5 or 6 minutes of an introduction on that. So I may actually have to get to the content sooner. But today we'll be discussing bringing data flow and warehousing together. So let that quote sit in for a second. I think it's important to go a little bit on my background. I've worked in warehousing for a number of years using Apache Accumulo. Worked with probably 2/3 of you, actually. So I think that what's important is that I understand the query, ingest, compaction workloads to a pretty decent degree. I understand the internals of Apache Accumulo reasonably well. I recently began working with Apache NiFi. Is there anyone in here who is not familiar with NiFi? That's fake because I know he knows NiFi. So that's great. It means I don't actually have to spend a significant amount of time discussing the internals to NiFi. What I actually work on, though, is Apache MiNiFi. Oops, cart got ahead of the course. I think it's moving it automatically. So Apache MiNiFi is broken up into 2 segments. There's a Java and a C++ API, or rather, agent. The C++ agent is what I work on. I do a little bit of work on the Java agent, but that's not necessarily what the focus is today. This is a complementary project which functions to augment Apache NiFi. That's important because it's very nuanced in that we are not trying to replace NiFi in any way whatsoever. Apache MiNiFi works directly with Apache NiFi. It's built on platforms x86, ARM, single board computers. This is important because the reason why Java doesn't work is not because it isn't fast enough. I think many people think that C++ is faster. It's not. It may have a smaller memory footprint, better startup, but the big issue is licensing. The JDK license does not work on many embedded devices without paying a rather high amount. So for commercial use, even Raspberry Pis, you end up spending on the order of 71 cents per unit. For the license, for the Oracle JDK license on other devices, it could be per core. So for many companies, it's become paramount that we move away from the JDK and move into the realm of C++. So today we'll be discussing Edge IoT. IoT is a very sexy word. I think that Aaron in the beginning mentioned this. What we're not doing today is doing a presentation because NiFi is going with Accumulo. Apparently I don't know how to use PowerPoint. So we're not doing this specifically to use NiFi because we want to introduce NiFi into the Accumulo Summit. What we're doing is we're looking at different ways of offloading resources. And the typical approach, I think, is edge collection, whether that be on a computer or a single board computer, and send data to the data warehouse. This may often occur through Apache NiFi. What we're hoping to do, though, is offload some of these resources to an idle cluster, or to offload this processing to idle resources. We want to perform as much as possible at the edge. The edge is simply a term we coined to mean the point at which data is collected. So this doesn't necessarily have to be a device in an automobile, your cell phone. It could be anything. It could be even within your own cluster. So in theory, it sounds good to move the collection and the ingest processing closer to the edge. But of course, there are risks in doing this, and we'll go over that a little bit. At the end, we'll go to a live demo, which I think maybe has a 30% chance of working. It worked earlier, but that does not mean it's going to work now. In fact, show of hands, who thinks it's going to fail? Nice. I have most of the, if you couldn't see, it was nearly the entire room. So let's look at this from the problem statement perspective. What is the problem that we're trying to solve? Well, IoT, the Internet of Things, is really just a term to mean any device from which data can be collected. This can be a box that you're collecting log information. It could be a Raspberry Pi. It could be your Arduino. What it does, though, is it fundamentally increases the amount of data that we're ingesting into our cluster. We can combine the data. We can go through various ingest pipelines. We can go through Spark. We can compact it earlier in the process. But of course, this increases latency, and we only have a finite amount of resources. Oh. I apologize. I have no idea what this is doing. Actually, let's see. So ingest, query, and compactions are always something we have to be cognizant of in our cluster. If we ingest more data, as Drew and Bill mentioned earlier, we may lead to more compactions. More compactions may slow down queries. Slower queries could ultimately increase compactions. It's almost as though we have a negative feedback loop. And you always think you have enough resources until you don't. So the thought here is that we hopefully offload resources to devices that are idle. Sorry, I have no idea what's going on. What we aim to address, we're not Google. So the point of this slide is to look at this from the perspective that we don't have infinite resources. Our IoT infrastructure is going to grow. The devices from which we collect will grow. And that gives us the ability to run processing on them, but we aren't Google in that we can't just add resources. Many of you may work with AWS or Google IoT or even Amazon IoT. There you do have the ability to spin up resources, but it comes at a cost. Usually additional resources, additional tablet service, for example, that's going to come at a cost. But that cost of doing business is generally not as acceptable as the cost of collecting that data. What I mean is that an organization may not necessarily care if we add more devices from which to collect because that is your job. Storing it in a cluster is not your job. That isn't necessarily as big of a deal. Most people in NiFi don't care about how the data is stored. Most people in Accumulo don't care about how the data gets there. So we're here today is to focus on both ends, bringing two products together that work in conjunction, hopefully alleviating issues on the warehouse side. So I'm going to try moving only one slide this time. So what are our options? We can increase capacity. As many of you are familiar with, you have read-ahead threads, you have master fate threads, you have compaction threads. All of these can be increased, but only up to a certain point. Amdahl's law teaches us that the most parallel processing is limited by our most serial point, which is generally I/O. Long and short is that we're effectively limited by what we can do through our I/O subsystems, and if we increase threading, we increase competition on those boxes. Adding tablet servers is the best idea. Obviously, if you can add tablet servers, you're going to do a much better job than if you were to increase threads or add some arbitrary box to do processing. But if you have the ability to outsource your edge resources, and later on there will be somewhat of an M. Night Shyamalan twist because what I'm discussing now doesn't really plays into this a little bit differently later because we have the ability to sort of run things in our cluster as we would at the edge. Every device that we have collects data, including Microsoft PowerPoint. I at my home have smart lights. I assume many of you do as well. The Philips Hue bridge that I have collects data, actually uses Apache NiFi, sends it to an intermediate cluster. That intermediate cluster is a gateway. That gateway goes to the cloud. Everything that we have collects data. While that light can also be a threat vector, it can also be how we get data to our information about our house. Cell phones, very obvious. That is an edge device that collects data. But another device, I've recently been working with some insurance companies in the automotive industry. Their goal, in fact, they said they're doing something very similar with HBase, so I thought, well, maybe this isn't a terrible idea. Their goal is to get data and process it in such a way that it can be directly imported into HBase. Most cars that you see, my car uses, I believe, OnStar. That's a very relatively weak system. GM doesn't have much processing power. But Mercedes, they actually have quite a bit of processing power. They can support many cores. They have a lot of capabilities on that box. So the point of this graph is that as we look at all of these devices, we have to be cognizant of the fact that every device, maybe not that lampshade or that lamp, but all of these devices have significant processing power. We can do more at the edge or where we collect that data. I have a lot of cameras in my house, and the previous generation of the products that I currently own actually had command and control capabilities for the company that built them. Theoretically, they could collect whatever they wanted to inside of my network and send that to some intermediate source such as NiFi. In fact, I believe they did because I was immediately told to stop using those devices. So the edge is simply, the point I want to impress upon everyone is that the edge is simply a term for data from the point at which we collect data. Typically, there is minimal processing or grooming, Typically, you send that raw data through NiFi, you send it to some source, you ingest it. You run your Spark jobs, or you run your MapReduce jobs. Or if you're gutsy, maybe you run some Yarn tasks. But Apache NiFi is generally the intermediate, at least in the scope of this talk, because why would I talk about stream sets? You may not have the compute capacity, and that's very important because devices sometimes are just simple sensor readers. Sometimes they're cell phones, computers, but we have to customize the workload to the capability. So as we get further into the presentation, I'll discuss how we do that, but I'll begin with some caveats that not all devices have persistent storage. One of the hallmarks, as you know, of Apache NiFi is that we have provenance, we have the ability to track these events. We don't always need that or want that. So edge devices, Raspberry Pi. I think that's the perfect example of what an edge device is not. Simply because it's actually a very powerful little computer. Most edge devices are somewhere in between sensor reader and Raspberry Pi. Your phone is a great example. Your phone right now is collecting massive amounts of data on you and sending it to Google or Apple. If you don't believe me, try Google Home. They know where I am, they knew where I was coming today, and they know where I'm going later on. And this is where the data originates. Devices, again, they may not support complex logic or have persistent storage, but as we get into the nuances of what we're going to be doing with Apache MiNiFi, that's an issue we've addressed through some mechanisms that are pretty cool, or at least I hope you find them cool. So edge latency. This graph is to sort of soften the blow about what we're going to be doing. And by that I mean, this comes with major caveats. If you have a network of 100,000 cell phones, back pressure is a major concern. You can only send so much data to your source. I think it was said probably much more eloquently by Bill that when you ingest a lot of data, you're going to cause compactions. Well, a similar concept I think exists in terms of sending it to any data source such as NiFi. If you slow down your processing at these edge devices, you of course increase the amount of data, you increase the amount of networking load, and you may not have the link speed or the processing, and you may cause back pressure. And that effectively means that you have slowed down the ultimate processing of your system. But you have to send data anyway. And in many cases, you have to groom data in some way. You have to put it into some structure and pass it along. IoT refers to many different things. I think IoT is a fantastic buzzword, but in the scope of this, I'm mentioning it because as we get into how we're using this, it's very important to realize that our network is beyond our warehouse. It is beyond the intermediate gateways that we have. Our network is actually well into automobiles, into boxes, whether you're doing it maliciously or not, whether you have control of these boxes, you effectively have unlimited processing capabilities beyond your network. I think one way that when I first arrived on MiNiFi, one of the things I coined was, this looks like we're trying to build a massive opt-in botnet. And that is exactly what we're building. Because MiNiFi C++, which does have a very small memory footprint, it also has a complex command and control facility. So the goal of that is that command and control is ever important if we are trying to ensure that we don't cause the problems that we saw on the previous slide. What I mean by that is we need to be able to communicate to NiFi instances and to MiNiFi instances. But we also need to ensure that we don't cause back pressure. And if we do, we need to roll back. We need to be able to do that automatically. And in order to do that, we need to have complete control of that device, or at least the process on that device. We need to be able to detect if problems occur. We need to be able to detect exactly how much is in a queue on a device that's 200 miles away. We need to be able to tell that device, which can only check in once a week because it's on LTE, that it needs to slow its processing down. We need to take a step back. So complete command and control is absolutely paramount. So the use case is that our IoT infrastructure grows, and so does our compute as a result. If the one thing you can take away from this is that MiNiFi, being just this massive botnet, being this distributed framework, allows us to run, along with NiFi, any arbitrary process that we want. So Apache MiNiFi has many of the same concepts that exist in NiFi. The C++ agent was built from scratch and is currently being built. GA will occur sometime in January. The Java agent again, is just a stripped down version of NiFi with the web server removed. But in many cases, the footprint for that is still much larger than many devices. Our goal is to run this in kilobytes. The demo, which, if it works, generally runs in 300 to 400 kilobytes at most. On average, we can run and create RFiles in 75 kilobytes. And the corresponding Java agent is megabytes plus. Again, this is the remote process groups, command and control, and processors are all a key component of MiNiFi in order to be able to support asking a question and ingesting data from the entire infrastructure perspective. And I think that the important thing about this quote is that when I started down this endeavor, it was pretty much a POC. So the goal was to try and take some of this processing that we're performing in our infrastructure, usually inside of our warehouse, and move it outside. As I mentioned earlier, why can't we just use NiFi? Well, we can. It pushes data better than salt and pepper. Push it, and it pushes it real good. It's used frequently, obviously, at various sites, including those warehouses and intermediate sites in which you send data to, and then they send data to the warehouse. But there are licensing and memory concerns. I would say that the memory is probably not as big as the licensing concern. Any device in which you own, typically as developers, most of them support the JDK license, but devices across the plethora that we saw within that image, many of those simply do not, or the cost is too high. So given what we've just said, and we've looked at the edge being any device on our network, being any device in our purview, we're going to leverage some of this compute capacity to do some work that we can do in the tablet server, or would always do in the tablet server. So what if we created RFiles outside of our warehouse? What if we made them at our device, compacted them at our devices, and intermediate devices? What if we used NiFi to load balance across various realms of networks and subnetworks and compacted them and sent more compact data to our warehouse? Obviously, that point probably doesn't resonate very well, but what I'm trying to say is that if we can do less in our ingest clusters, more in our edge devices, and compact more, we can potentially reduce compaction storms, query impact as a result of those compaction storms, and hopefully scale our architecture up dramatically based on the number of agents. So what we'll do is we'll discuss, I'll go through some of these processors that I've built and how we built them, and in the demo, we'll actually see these running in real time. So hotspotting and an influx of data is typically some of the problems that we see when we have compaction storms. And I assume everyone's familiar with the compaction storm, but if you aren't, as you have a lot of data coming in and you have an increase in query load, compactions may actually cause problems with access to that data. As I mentioned earlier, that is almost a negative feedback loop. You have a lot of ingest and query load impacting compactions. So if we can offload the creation of these RFiles and compactions outside of our cluster, we can potentially use more of it for the query of that data. The final point is in that compactions are a necessary process is that we can't stop compactions from occurring. They will always occur. But the goal here is that we do more in our infrastructure that is idle. So doing more at the edge definitely has risks. We lose fidelity of our data. And by that I mean if we, instead of sending raw data to our NiFi instance then to our cluster, and we compact it there, we may lose some information, especially if there are errors. Command and control helps with this in that we can always make software changes real time, but you're always going to lose fidelity of your data. And you may not want to send business logic to your edge devices. You may not be able to. Security is always the potential risk that you don't want to put your business logic out there. So not all options are available for these reasons, but also for networking restrictions. As I mentioned earlier, in automobiles, they typically have LTE and Wi-Fi devices. Wi-Fi, we can send a lot of data, but with the LTE, we may be limited, and we may have bandwidth caps. Companies don't necessarily want to spend a lot of money transmitting data, which is why OnStar uses very, very small packed structures to send their data. So MiNiFi C++ is written in C++. I also have, around 4 or 5 years ago, I started on a C++ client that's completely native, no proxy. Here we're using that as a plugin. I stopped development of that around September last year. The goal is to move some of these T-server operations to the edge. These two agents working together, or rather, these two libraries working together, allow us to create RFiles within the MiNiFi agents on any device. And what I mean by this point about accessing Zookeeper being cray-cray is that in most cases, if we're on an edge device, we don't have access to Zookeeper. We don't have access to that part of our cluster. So typically what we would do in the normal use case is send our files to a NiFi instance, redistribute them, compact them into classes of tablet server buckets specifically for a T-server, and then import them elsewhere. So creating RFiles obviously requires data to be sorted. So this means that in an agent, we may not have sufficient memory to do a lot of work. So this is very use case specific. In the Raspberry Pi, you can do quite a bit of work. On a general purpose computer, you can do even more work. But we want to minimize the crossing tablet boundaries, hence why in this very small graph, you can see that we have at least one output port. But in a typical demo case, we would have many output ports so that we minimize the crosstalk across tablet boundaries. The goal here is to keep memory for agents generally around 4 megabytes. We can keep it much lower, but the reason why 4 megabytes is important is we'll get to later that you don't necessarily always have to use your edge devices to do the work. Your edge devices could be a Docker instance within a cluster. So we'll get to how we've used Docker Storm specifically, to be able to spin up a large number of instances and run anything we want in Apache MiNiFi. So one thing that we've done here is to try and minimize the memory footprint. We've used relative key encoding in a memory structure so that since most data-generated edge devices is linear, we can maximize in-memory structures so that we minimize how much is actually stored in memory before we spill it to our flow file. So this is important because this doesn't apply to everyone, but if your keys are very linear, if you apply the techniques that are used in RFiles to memory, in many cases I've been able to reduce the number of RFiles dramatically simply because we have much denser RFiles. Since I had to have some color beyond the footer, I made this. So at the MiNiFi agents, we're running our RFile and site-to-site, which ships data into NiFi. We receive that data at other MiNiFi instances, compact those RFiles, and when we redistribute it and import it at our gateway. So I've written 3 processors, the Accumulo writer, bulk importer, and compaction processor. The Accumulo writer simply takes data, stores it in memory into the relative key structure, and writes it at a threshold. It takes the data from the flow files and puts that into the value. This is simply to demonstrate the worst case scenario of Accumulo, where you have a rather large value in relation to the size of your key. In this processor, we actually have no need for Zookeeper. In the compaction processor, it functions much like the compaction thread in the T-server, but it's much more limited in memory. And we don't run the iterator stack simply because at edge devices, we don't need to. Zookeeper is not required here. But it's important to note that if we're to do work like the compactor, we have to be aware that whatever data we're sending to our cluster, we can only do it in the confines of the memory footprint that we've prescribed for our MiNiFi agents. And finally, the bulk importer does what I said not to do, which connects to the Zookeeper quorum. This uses Zookeeper, and it's better to be done in NiFi, but for the purposes of this demo, I wanted to show MiNiFi agents importing to the cluster. And this is important because this is the use case where this works in Docker, and I'll get to that in the next slide. It simply creates the failure and import directories and bulk imports those RFiles to Accumulo after we've compressed them, or compacted them rather. So one of the people with which I work took Docker Storm and ran thousands of MiNiFi agents. He did that in probably about 16 gigabytes of RAM. What's important is he did this across a cluster. He didn't use command and control, but it showed a very important use case, I think, that I hadn't even considered, which is that when we look at this MiNiFi agent running on edge devices, as I mentioned earlier, an edge device could be the computer, it could be your cluster itself. You could use Yarn, you could use Tez. You probably don't want to use Tez. Or Yarn. You could use MapReduce. You could use various other buzzwords to bring your data together. But being a general purpose framework, MiNiFi works very well because we aren't concerned with scheduling. We use the load balancing in NiFi to do the scheduling, and we allow command and control to control what we're doing within our devices. Since most of these devices, in fact, we actually use this in our test framework, in our system integration test framework, and I think that's very useful because it shows that all of our tests cap out at 4 megabytes. That's the limit we set for them. That is an arbitrary watermark. There's no reason why you couldn't go higher. But in most cases, you don't need to run more than a few megabytes. So you can, on your cluster, run thousands of MiNiFi agents performing whatever task you need within minutes using Docker Storm. Oh, I hear the lunch cart's coming. So hopefully, I'm going to try and start the demo. If it doesn't work, then that means early lunch. In the meantime, are there any questions? Oh, that update's very important. Okay. So first of all, hopefully I haven't gone to any sites that I don't want you to see. All right, so we have an EC2 instance running. So in most cases, I apologize, I didn't expect so this is a very contrived example because I wanted to increase the likelihood that this would actually work. So I have simply one instance with a few MiNiFi agents. Here we have okay. I didn't develop this GUI, nor is this the GUI that will be used. This is simply a developer GUI. I'm using this here without fear that you will make fun of me, but this is our command and control interface currently. NiFi proper has much better UI developers. They do not include Mark, and therefore I will not be part of that. So with that caveat in mind, what we're going to do is we're actually going to, I have a demo where I spin up a cluster, but here I'm actually just going to spin up Mike Wall's standalone Mac. And while we have other MiNiFi agents, oops, we've already had failure. So this, just to show you, give you some perspective, this is the configuration file. Typically humans wouldn't see this, but we're beyond human here. So we're going to generate a flow file, utilize the Accumulo writer, bulk import, and apparently in this demo we're also going to scan. All right. So theoretically, our NiFi instance, we should begin seeing something happen. Oh look, we have 7 new flow files. So as we open up this RPG and we enable it, this MiNiFi agent, which is currently running 73 kilobytes, 300 kilobytes. Oh, and it failed, so that's perfect. Actually, I think it failed because I did something early, but actually, maybe everyone can hear me if I put this down. What we want to see is that it actually inserted data. And what's important here, if this actually works, is that we have data coming out in our log attributes. So to give you some perspective of what this is probably hard to follow, right now we're creating data from our NiFi instance and writing the RFiles directly from the C++ agent. We're sending this to NiFi, and we're scanning for those keys and sending them directly to the log attribute. All that does is simply log the fact that I don't know if I have this. I'll open this up directly, but log attribute simply takes those keys and writes them out. The importance of this is that while this is all running on the same EC2 instance, it doesn't have to be. In this demo, we're actually not compacting, but I do have another demo I can show you if you want to afterwards. In this demo, we're writing to the RPG to MiNiFis so that we can bulk import them. That bulk imports into our standalone Mac from Accumulo is the data that's received as a result of scanning Accumulo. And theoretically, we could do whatever we need to at that point. As you can see that in most cases, we're kind of overwhelming this instance because we're sending quite a bit of data, quite a number of keys in individual flow files. But in most cases, this is a relatively contrived example to show that we can actually run a general purpose framework. In most cases, I wouldn't advise doing this unless you have significant infrastructure. But as I said, this was a POC to show that we can run virtually any type of processing in our framework without concern for memory or licensing concerns. All right, does anyone have any questions? I think that's, I'll stop boring you.
Talk about a risk of data loss.
Sure.
Is there any was there anything being talked about implemented to reduce that risk at all?
The risk, the only real way to account for that is if you send your data. If you were to write RFiles, for example, you could do live ingest and bypass that concern. But if you were to write RFiles, you would also have to send that original data through NiFi. So that increases your networking throughput, or load rather. So I think that's the important key, is that if you don't have capacity to send that data, the raw data, you may lose fidelity. Incidentally, RFiles actually work to compress data very well. So I'm not sure that's always the case, but if you're sending small amounts of data, depending on the periodicity of that data, you may or may not be reducing the size of it. Anyone else? Well, thank you for your time.